When we gaze into the night sky, we see the brilliance of stars and the gentle swirl of distant galaxies. The universe often feels alive, a realm of boundless energy and perpetual change. It is a place of serene beauty, a calm cosmos that has unfolded over billions of years, giving rise to structures of breathtaking complexity. We see the soft glow of nebulae where new stars are being born, and we trace the ancient light from galaxies so far away that we are looking back into the distant past. This universe, our home, feels eternal, a constant and reassuring presence. But what if there is another side to this cosmos? A future that is still, silent, and frozen in an eternal winter? What if the very laws that allow for the brilliant fire of stars and the warmth of life also decree that this fire must one day burn out, leaving nothing but a profound and unending chill? Tonight, we embark on a journey to the coldest, most desolate corners of existence. We will travel forward in time, far beyond the last glimmer of the last star, to witness the universe in its final state. This is the story of the frozen cosmos, a universe that has exhausted its fire and is draped in a final, silent darkness. We will explore the fundamental principles that govern this destiny, witness the slow decay of stars and galaxies, and contemplate what it means for everything to end. This is not a story of sudden cataclysm, but of a slow, graceful, and inexorable descent into perfect, absolute calm. The story of the universe's ultimate fate is not written in the stars, but in a law far more fundamental, a principle that governs everything from a cooling cup of tea to the expansion of the cosmos itself. This is the second law of thermodynamics, and it is one of the most profound and unyielding truths in all of physics. In its simplest form, it states that in an isolated system, the total amount of disorder or entropy will always increase over time. Energy, left to its own devices, tends to spread out, to move from a state of useful, concentrated order to a state of useless, dispersed disorder. To truly grasp this, let us step away from the cosmic scale for a moment and consider something familiar. Imagine a perfectly ordered sandcastle on a beach. It is a structure of low entropy. The sand grains are arranged in a specific complex pattern. Now imagine the effects of the wind and the waves. Over time, they will inevitably break down the castle, scattering the sand grains randomly across the beach. The system moves from order to disorder. The energy of the wind and waves is used to increase the entropy of the sandcastle. It would be utterly astonishing, bordering on miraculous, if the random motion of wind and waves were to spontaneously form a sandcastle from a flat beach. The universe works in the same way. It moves in one direction, from order to chaos. The universe itself began in a state of incredibly low entropy. At the moment of the Big Bang, all the energy and matter of the cosmos were concentrated into an infinitesimally small, hot, and dense point. This was a state of perfect, or at least near perfect, order. This initial low entropy state is the ultimate source of all the order and complexity we see today. It is the cosmic sandcastle from which everything else has emerged. The expansion of the universe from this point onwards has been a process of this initial, concentrated energy spreading out and transforming. This spreading of energy is what allows anything interesting to happen at all. It is what drives the flow of time forward. We remember the past and not the future, because the past is where entropy was lower. The arrow of time is, in a very real sense, the arrow of increasing entropy. A broken egg doesn't spontaneously reassemble itself. Perfume released from a bottle doesn't gather itself back in. These are all everyday manifestations of the second law. Now, let us apply this to the cosmos. Stars, like our sun, are magnificent engines of order. They take chaotic clouds of gas and dust and, through the force of gravity, compress them into highly ordered spheres. Inside their cores, they perform the miracle of nuclear fusion, creating heavier elements and releasing immense amounts of concentrated energy. This energy radiates outwards, and a tiny fraction of it might be captured by a planet like Earth, creating a local pocket of even greater order, the intricate chemistry of life. We, and everything we have ever known, are temporary, beautiful structures built by fighting against the tide of entropy, powered by the low entropy energy provided by our star. But this process is inherently temporary and wasteful. For every photon of sunlight that strikes the Earth and powers life, billions upon billions are radiated out into the cold, empty void of space, never to be used for anything. The sun is, in effect, burning its low-entropy fuel and converting it into high-entropy, disordered heat and light that spreads out across the cosmos. Every star in every galaxy is doing the same. They are all contributing to the slow, steady increase of the universe's total entropy. They are magnificent, but they are also cosmic bonfires, burning through the universe's inheritance of order. The second law dictates that this process cannot go on forever. The universe has a finite amount of usable energy, a finite amount of order. Eventually, all this energy will have spread out as much as it possibly can. A time will come when the temperature and energy distribution of the entire cosmos becomes uniform. There will be no more hot spots and no more cold spots. No more stars shining brightly against a dark sky. There will only be a vast featureless expanse where every point is at the same, near absolute zero temperature. This is the state of maximum entropy. This is thermal equilibrium, and this is the state known as the heat death of the universe. The term heat death is somewhat misleading. It does not imply a fiery end, but rather the complete absence of heat flow. Heat is only useful when it can flow from a hotter object to a colder one. This flow is what allows work to be done. It's what drives engines, powers chemical reactions, and makes life possible. In a universe at thermal equilibrium, there is no heat flow, there is no hot and no cold. There is only a uniform, lukewarm, or rather ice-cold soup of diffuse particles. In such a universe, no work can be done. No complex structures can form or sustain themselves. All meaningful processes would cease. This concept can feel deeply unsettling. It paints a picture of a future that is not just empty, but static and unchanging. It suggests that the entire glorious history of the cosmos, the formation of galaxies, the birth of stars, the evolution of life, the rise of consciousness, is just a temporary phase, a fleeting burst of complexity in a universe whose ultimate destiny is simple, featureless uniformity. From a philosophical perspective, the law of entropy forces us to confront the ultimate impermanence of everything. The grandest structures we can imagine, from spiral galaxies to superclusters, are no more permanent than a sandcastle on the beach. They are all subject to the relentless one-way march of time and decay. The universe is not a steady state. It is a process, an unfolding story with a beginning, a middle, and an end. And the second law of thermodynamics is the author of that final chapter. It is a profound and humbling realization. The energy that animates us, the light by which we see, the very thoughts we're thinking right now, all are temporary manifestations of a cosmic energy gradient that is slowly but surely flattening. We are living in the vibrant, dynamic phase of the universe's life. We are born of the universe's initial order, and we are witnesses to its magnificent ongoing transformation. But the law is not a curse. It is simply a description of reality. There is a strange, cold beauty in its impartiality. It is the silent, invisible force that orchestrates the grand cosmic ballet, ensuring that the universe has a direction, a history, and a destiny. It is the reason the cosmos is not a static, boring crystal, but a dynamic, evolving entity. The journey from low entropy to high entropy is the journey of the universe itself, and as we continue our exploration into the frozen cosmos, we will see the consequences of this law play out over timescales that defy human comprehension, shaping the final, silent fate of space and time. The inevitable end is not a failure, but the logical conclusion of the universe's own fundamental nature. It is the ultimate return to calm. Before we journey into the profound cold and darkness of the distant future, it is essential to pause and appreciate the universe as it is now. We live in a golden age, a brief and brilliant cosmic springtime known as the stelliferous era, the age of stars. This is the universe we know and recognize, a cosmos filled with light, warmth, and the intricate dance of gravity and matter. It is the only era in the universe's long history where the conditions are right for the emergence of complexity, for the formation of planets, and for the miracle of life. The stelliferous era began a few 100 million years after the Big Bang. The early universe was a dark, formless expanse of hydrogen and helium gas, a period aptly named the Cosmic Dark Ages. But gravity, the patient sculptor of the cosmos, was already at work. It began to pull these vast, diffuse clouds of gas together, drawing them into ever denser clumps. As these protogalactic clouds collapsed, the pressure and temperature at their cores began to rise until a critical threshold was reached. The first stars ignited, flooding the universe with light for the very first time, and bringing the cosmic dark ages to a spectacular end. This is the universe we inhabit today, a cosmos dominated by the light and energy of stars. When we look up at the night sky, every point of light we see, from the nearest star to the most distant galaxy, is a testament to this era. Stars are the engines of the cosmos, the crucibles where the elements of life are forged. They are immense nuclear furnaces, converting simple hydrogen and helium into the carbon, oxygen, nitrogen, and iron that make up our world and our bodies. As the astronomer Carl Sagan famously said, "We are made of star stuff." This is not just poetry, it is a literal truth. Every atom in your body, other than the primordial hydrogen, was created in the heart of a star that lived and died long before our sun was born. The stelliferous era is characterized by a hierarchy of structure. Stars are not scattered randomly throughout space. They are gathered by gravity into immense majestic islands of light we call galaxies. Our own Milky Way is a typical spiral galaxy, a swirling disk of over 200 billion stars rotating slowly in the darkness. And our galaxy is just one of hundreds of billions, perhaps even trillions, in the observable universe. These galaxies are themselves gathered into clusters and superclusters, vast filaments of matter stretching across millions of light years, separated by immense dark voids. This cosmic web is the grand architecture of the stelliferous era. There is a profound calming beauty in this structure. It is a perfect balance between the explosive energy of stars and the persistent, organizing force of gravity. The universe is not a chaotic, random explosion. It is a system of nested harmonies, from the elegant orbits of planets around a star to the stately rotation of stars around a galactic center, to the slow, gravitational waltz of galaxies within a cluster. It is a cosmos of cycles. Stars are born from interstellar clouds, they live for millions or billions of years, and when they die, they enrich the cosmos with new elements, seeding the next generation of stars and planets. It is a self-sustaining cosmic ecosystem of creation and renewal. This era is special because it is a time of gradients. As we explored, the universe is governed by the flow of energy from hot to cold, from order to disorder. The stelliferous era is the peak of this activity. Stars create immense temperature gradients. Their surfaces are thousands of degrees, while the space between them is near absolute zero. It is this very gradient that allows for interesting things to happen. A planet orbiting a star exists in a sweet spot, bathed in a constant stream of low entropy energy. This energy can be harnessed to drive complex processes. On Earth, it powers photosynthesis, drives the weather, and provides the warmth necessary for liquid water to exist. Without the energy gradient provided by our Sun, Earth would be a frozen, lifeless rock. Life, in its essence, is a temporary rebellion against the second law of thermodynamics. It is a process that takes in disordered materials from its environment and, using a flow of energy, organizes them into highly complex, low-entropy structures. An organism is a marvel of intricate order, from the precise folding of a protein to the complex neural network of a brain. But this order is maintained at a cost. To build and maintain itself, every living thing must consume low-entropy energy and expel high-entropy waste. We eat food and radiate heat. We are local pockets of decreasing entropy, made possible only by contributing to the overall increase of entropy in the universe. Thus, the stelliferous era is the only era that can host life as we know it. The earlier universe was too hot, too dense, and lacked the heavy elements necessary for complex chemistry. The future universe, as we will see, will be too cold, too dark, and too empty. We are living in a fleeting, privileged moment. The conditions that make our existence possible, a stable star, a planet with liquid water, a rich supply of chemical elements, are a product of this specific cosmic age. The timescale of this era is vast, almost beyond human comprehension, yet it is finite. The smallest, faintest stars, known as red dwarfs, are incredibly fuel efficient. They sip their hydrogen fuel so slowly that they can shine for trillions of years. The estimated lifespan of the stelliferous era is therefore around 100 trillion years, a time when the last red dwarf finally exhausts its fuel and fades to black. While this is an immense span of time compared to the current 13.8 billion year age of the universe, it is but a brief flash when measured against the true timescale of eternity. Contemplating this can evoke a sense of cosmic vertigo. Our lives, our civilizations, the entire history of humanity have unfolded in a fraction of a second on this cosmic clock. We are a brief flicker of consciousness on a tiny planet, orbiting an average star in one of countless galaxies during the universe's vibrant youth. But this perspective should not lead to a feeling of insignificance. Rather, it should inspire a profound sense of wonder and appreciation. To be alive now is to win a cosmic lottery of unimaginable odds. We are witnesses to the universe in its most glorious phase. We have the privilege of looking out into the cosmos and seeing it not as a cold, empty void, but as a glittering tapestry of light and life. We can trace the constellations, wonder at the phases of the moon, and feel the warmth of a sun that is just one of billions, yet is everything to us. The calm of the cosmos we see today is the calm of a deep and powerful engine running smoothly. It is the peace of a system in a state of dynamic, creative equilibrium. It is a universe still full of potential, still actively creating, still shining. The silence of space is not one of emptiness, but one of immense scale and patience. The processes we see are slow, deliberate, and majestic. The formation of a star, the collision of galaxies, the long journey of light across the void, these are events that unfold on timescales of millions and billions of years. So, as we prepare to leave this luminous age behind and venture into the deep future, let us hold this image in our minds, the image of a spiral galaxy, a river of stars flowing through the darkness, the image of a blue-white planet teeming with life, the image of a sky ablaze with light. This is the calm cosmos. It is our home, our cradle, and our reference point for the long, cold journey ahead. It is the brilliant, beautiful exception in a universe whose ultimate fate is to be dark, empty, and still. The memory of this light will be our only guide as we step into the eternal twilight that awaits. Our journey now takes us across a threshold of unimaginable finality. We travel forward in time, past the lifespan of our sun, past the age of the oldest galaxies, to a moment around 100 trillion years from now. Here, we witness the end of the stelliferous era. The smallest, most frugal stars, the red dwarfs that have glowed faintly for eons, finally exhaust their vast reserves of hydrogen. One by one they flicker and die, their ancient light fading into the encroaching darkness. The last star in the universe goes out. The age of stars is over. The cosmos is plunged into a darkness it has not known since before the first stars ignited. The sky, from any vantage point, is now an endless, unbroken black. The great beacon fires of the universe have been extinguished, leaving behind only their cooling embers. We have now entered the degenerate era. The name sounds bleak, but in physics, degenerate refers to a specific state of matter that has been crushed by gravity to its absolute physical limit, a state where quantum mechanics, not thermal pressure, is what holds it up against total collapse. This era is the age of these stellar corpses, the degenerate remnants of the once bright stars. The universe is now a cosmic graveyard, populated by three main types of objects. The first are the white dwarfs, the remnants of stars like our Sun. After exhausting their fuel, these stars shed their outer layers, leaving behind a dense, Earth-sized core of carbon and oxygen. A white dwarf is so dense that a single teaspoon of its material would weigh several tons. They are born incredibly hot, shining with a brilliant white light, but with no fuel left to burn, they simply cool. Over trillions and trillions of years, they will fade from white to yellow, to orange to red, until they emit no visible light at all. They will become black dwarfs, cold, crystallized spheres of degenerate matter, floating like ghosts in the eternal night. They are, in essence, colossal diamonds in the sky, though no light will ever shine upon them. The second type of remnant are the neutron stars. These are the relics of much more massive stars, those that ended their lives in spectacular supernova explosions. What remains is a city-sized sphere so dense that it is essentially a single giant atomic nucleus. A teaspoon of neutron star material would weigh billions of tons. The gravity on their surface is so intense that it crushes atoms themselves, forcing electrons and protons to merge into a sea of neutrons. Like white dwarfs, they are born hot and spinning rapidly, but they too will cool and slow down, their immense energy bleeding away into the void until they become cold, silent, and invisible. Finally, there are the black holes. These are the ultimate victors of the gravitational war. Formed from the collapse of the most massive stars, or lurking as supermassive behemoths at the centers of galaxies, they are regions of spacetime where gravity is so strong that nothing, not even light, can escape. In the degenerate era, they are the dominant gravitational players, patiently waiting in the darkness. The universe of the degenerate era is dark, but it is not static. The processes that now unfold are driven not by the fiery energy of fusion, but by the slow, inexorable, and patient pull of gravity, playing out over timescales that make the entire stelliferous era seem like a fleeting moment. The galaxies as we know them will begin to dissolve. The beautiful, orderly spiral arms of the Milky Way are a temporary feature. Over trillions of years, the stable orbits of the stellar remnants will be disrupted by close gravitational encounters. Imagine two black dwarfs, two dead suns drifting through the dark. Their paths cross, and while they may not collide, their gravitational interaction alters their trajectories. One might be flung into a higher, more distant orbit, while the other falls deeper toward the galactic center. This process, known as violent relaxation, will slowly change the shape of galaxies. The well-ordered disks will evaporate, their constituents scattered. Some remnants will be ejected from the galaxy entirely, cast out into the lonely intergalactic void, destined to wander in solitude for eternity. The majority, however, will be drawn inward, spiraling slowly toward the supermassive black hole that lies sleeping at the galaxy's heart. The universe is slowly cleaning house, with gravity as the cosmic broom, sweeping the stellar embers into piles, or casting them into the void. Even in this profound darkness, there may be moments of unexpected final light. Consider two white dwarfs that have been orbiting each other for trillions of years as a binary pair. As they circle one another, they create tiny ripples in the fabric of space-time known as gravitational waves. These waves carry away orbital energy, causing the two dead stars to spiral ever closer. For eons, they perform this silent gravitational dance, their orbits decaying imperceptibly. But the final moments are swift and violent. They merge. If their combined mass exceeds a critical limit, known as the Chandrasekhar limit, the sudden compression can reignite nuclear fusion in the carbon and oxygen. The result is a cataclysmic explosion, a Type 1 supernova. For a brief, brilliant instant, a flash of light illuminates the darkness, a light brighter than a billion suns. It is a final, defiant firework in a universe that has forgotten light. It creates new heavy elements and blasts them into the void, but these events will be extraordinarily rare. An observer in what was once the Milky Way might only witness such an event once every few quadrillion years. They would be lonely, isolated beacons in an overwhelming ocean of blackness. Another, even stranger possibility involves the very nature of matter itself. Our current understanding of physics, embodied in the Standard Model, suggests that protons, the fundamental building blocks of atomic nuclei, are perfectly stable. But some more advanced theories, known as grand unified theories, predict that this may not be the case. These theories suggest that protons can, in fact, decay, though over an almost incomprehensible timescale of perhaps 10 to the power of 36 years or more. If proton decay is real, it represents a fundamental unmaking of the universe. It means that all the matter we know, the black dwarfs, the neutron stars, the planets, and any stray atoms, is ultimately unstable. Over these vast timescales, the very substance of the cosmos would dissolve. A black dwarf, that great crystal diamond, would slowly evaporate, atom by atom, into a sea of lighter particles like positrons and photons. The process is unimaginably slow. It is not an explosion, but a gentle fading as the fundamental components of reality itself unravel. If this is the universe's fate, then the degenerate era will be an age of ultimate dissolution. All the intricate structures forged in the hearts of stars and assembled by gravity will simply come undone. The universe would be slowly returning to a simpler state, erasing the legacy of the stelliferous era. The cosmic graveyard would itself turn to dust, and that dust would turn to faint radiation, leaving behind a universe even, emptier than before. In this scenario, The only things that would survive this great decay are the black holes. This vision of the degenerate era is one of profound loneliness and slowness. The distances between objects will be immense, and the time between significant events will be staggering. It is a universe where the primary force is a patient, grinding gravity, and the primary sound is a deep, cosmic silence. It challenges our perception of time and change. The universe is still evolving, but on a clock that ticks once every trillion years. There is a deep philosophical calm to this era. The frantic energy of the age of stars is gone. The universe is no longer in a hurry. It is settling into a long, quiet retirement. The processes are elegant in their simplicity, governed by the pure and unwavering laws of gravity and, perhaps, particle physics. It is a universe stripped down to its bare essentials. As we stand at the end of this era, looking forward, the cosmos is a far simpler place. If protons have decayed, the universe is now almost a perfect vacuum, containing only black holes and a diffuse low-energy gas of radiation. If protons are stable, the universe is a vacuum containing black holes and a scattering of cold, inert black dwarfs and neutron stars. In either case, the stage is now set for the final, longest reigning monarchs of the cosmos. The degenerate era fades, and the black hole era is about to begin. We now drift into the most enigmatic and longest-lasting period in the history of the cosmos, the black hole era. The universe has been swept clean. The last star has long since faded, and the degenerate era has concluded its slow, gravitational sorting. Trillions upon trillions of years have passed, a duration so immense that the entire 100 trillion-year stelliferous era is now just a distant, fleeting memory. The cosmos is now a realm of profound emptiness and silence, a near-perfect vacuum punctuated only by the most extreme objects that gravity can create. This is the age when black holes reign supreme. Depending on the ultimate fate of the proton, the universe at this stage takes one of two forms. If protons have decayed, as some theories predict, then all ordinary matter has dissolved. The black dwarfs, neutron stars, and stray planets have all evaporated into a thin, featureless soup of low-energy particles. In this scenario, the universe is truly empty, save for the black holes themselves. They are the last remaining macroscopic objects, solitary gravitational titans adrift in an endless void. If protons are stable, then the stellar remnants of the degenerate era, the cold, dark spheres of crystallized carbon and inert neutrons, still exist. However, over the preceding eons, gravity has continued its patient work. Most of these objects have been either ejected into the intergalactic abyss, or more likely, have spiraled into the waiting maw of a black hole. The universe is still a vast, dark space, but it is dotted with these scattered, inert husks of matter, along with the colossal black holes that have consumed their brethren. For the purpose of our journey, the distinction is almost academic, as the black holes are the undisputed masters of this age, the central characters in the final act of the cosmic drama. Imagine the scene. The expansion of the universe has continued unabated. The distances are staggering. The supermassive black holes that once sat at the centers of galaxies are now separated by gulfs so wide that light would take trillions of years to cross them. From the vicinity of one black hole, the sky would be utterly and completely black. There would be no other sources of light, no visible objects, nothing to indicate that anything else exists in the entire cosmos. The universe has become an archipelago of isolated singularities in an ocean of nothingness. What is a black hole? It is a destination of no return. It is a region of space-time where gravity has become so overwhelmingly powerful that it has, in a sense, broken the fabric of reality. Its edge, the event horizon, is not a physical surface, but a boundary of information. Once anything crosses that line, a stray particle, a beam of light, a dead star, it can never leave. Its information is, for all practical purposes, lost to the outside universe forever. The black hole is the ultimate prison, the perfect vault. During the black hole era, these objects are largely dormant. Having consumed most of the matter in their vicinity, they simply sit in the darkness, their immense gravity silently warping the space around them. They are the universe's final repositories of mass and complexity. The history of entire galaxies, the stories of billions of stars, the elements they forged, the planets they nurtured, is now locked away behind their event horizons, compressed into an infinitesimal point of infinite density known as a singularity. This era is the epitome of calm. The frantic energy of the Big Bang and the creative fire of the stelliferous era are long forgotten. The slow gravitational dance of the degenerate era has concluded. Now there is almost no change. The universe is in a state of deep, cold stasis. Time, in a meaningful sense, has almost stopped. With so few events occurring over such vast stretches of space, the passage of moments becomes almost irrelevant. The universe is holding its breath. But even this state of perfect stillness is not eternal. The most revolutionary idea in modern physics suggests that even black holes, the most permanent objects imaginable, are not forever. This idea comes from the work of Stephen Hawking, and it is known as Hawking radiation. It is a concept born from the strange and beautiful marriage of general relativity, the theory of gravity and quantum mechanics, the theory of the very small. In the quantum world, the vacuum of space is not truly empty. It is a seething foam of virtual particles, pairs of particles and antiparticles that pop into existence for a fleeting moment before annihilating each other. They're a constant underlying hum of reality. Hawking realized that if a pair of these virtual particles were to appear at the very edge of a black hole's event horizon, a strange thing could happen. It's possible for one particle to fall into the black hole, while the other escapes into space. From the perspective of an outside observer, it would appear as though the black hole is emitting a particle. Because the escaping particle has positive energy, the particle that fell in must have had negative energy to balance the cosmic books. This negative energy is subtracted from the black hole's total mass. The effect is that the black hole slowly, incredibly slowly, loses mass. It evaporates. This process is unimaginably inefficient. For a black hole the mass of our Sun, the rate of evaporation is so slow that it would take around 10 to the power of 67 years to disappear completely. For the supermassive black holes at the centres of galaxies, which are millions or billions of times more massive, the timescale is even more staggering. A large one might take 10 to the power of 100 years, a number known as a googol, to evaporate. Let us try, for a moment, to comprehend that number. A googol is a one followed by 100 zeros. There are not a googol atoms in the observable universe. There are not a googol grains of sand on all the beaches of all the planets that have ever existed. If you were to count from 1 to a googol at a rate of 1 billion numbers per second, you would not finish before the universe itself had completed its entire stelliferous and degenerate eras many times over. The black hole era is an age whose duration is, for all human purposes, indistinguishable from eternity. During this immense span of time, the black holes are like cosmic glaciers, slowly melting into the void. They radiate a faint, cold thermal glow. The smaller the black hole, the hotter it is, and the faster it evaporates. The larger it is, the colder it is, and the slower it evaporates. The supermassive black holes of this era have a temperature that is only a tiny fraction of a degree above absolute zero. Their radiation is a slow, methodical leak of energy into the empty universe. This concept has profound philosophical implications. It means that nothing is truly permanent. Even the ultimate prison of a black hole cannot hold its secrets forever. The information that fell inside, the matter of stars, the light of galaxies, is eventually returned to the universe, albeit in a scrambled, randomized, and utterly useless form as low-energy thermal radiation. The second law of thermodynamics holds true even here. The ordered information that was a star is converted into disordered high-entropy radiation. The universe continues its inexorable march toward uniformity. As a black hole evaporates, it loses mass, and as it loses mass, its temperature increases and it evaporates faster. For nearly the entirety of its googol-year lifespan, this process is imperceptibly slow, but the final moments are dramatic. In its last few million years, a supermassive black hole will have shrunk to the size of a mountain, then a house, then a grain of sand. As it shrinks, its temperature skyrockets. In its final second, having shrunk to a microscopic size, it radiates away its remaining mass in a final, brilliant flash of high-energy gamma rays. Imagine the scene one last time. In the utter absolute darkness of the empty cosmos, a point of light appears. It erupts with the energy of millions of hydrogen bombs a final silent firework that illuminates the void for one last glorious instant. And then it is gone. The black hole has vanished. One by one across the impossibly vast and expanding universe, each black hole will complete its long life and meet this same fate. The smaller ones will go first, followed by the stellar mass ones, and finally, after a near eternity, the last of the supermassive giants will erupt in its final blaze of glory. With the evaporation of the last black hole, the black hole era comes to an end. The universe has now shed the last of its macroscopic structures. The final repositories of matter and order have been returned to the cosmos as disordered energy. The slate has been wiped clean. The universe is now ready for its final and perhaps eternal state of being. We are on the cusp of the dark era, the ultimate end of all things. We have arrived at the end of the cosmic story. The black hole era has drawn to a close with the final, brilliant flash of the last evaporating black hole. The universe is now older than our minds can rightfully comprehend, perhaps a Google years old or even more. The stage is now empty, the actors have all taken their bows, and the lights have been turned off for good. We have entered the final age of the cosmos, the dark era. What is the universe like in this ultimate future? It is a place of almost perfect simplicity. It is a vast, ever-expanding and unimaginably dilute sea of fundamental particles. The only things that remain are the final, stable products of all the decay and evaporation that has come before. Photons of immense wavelength, neutrinos, electrons and positrons, all drifting aimlessly through the near-perfect vacuum. The temperature of the universe is now infinitesimally close to absolute zero, but not quite zero. It is a uniform, featureless expanse. There are no structures, no stars, no galaxies, no black holes, no atoms. The very concept of a place has become tenuous. The expansion of space has stretched the wavelength of the photons so much that their energy is almost non-existent. The particles are so far apart that the chance of any two of them interacting is practically zero. They are destined to drift alone, in the dark, for the rest of eternity. In this state, time itself becomes a deeply ambiguous concept, the arrow of time, which we experience as the direction of increasing entropy has lost its meaning. The universe has reached a state of maximum entropy. It is as disordered as it can possibly be, with no processes occurring, no heat flowing, no change taking place. What is there to mark the passage of time? The cosmic clock has not just slowed down, it has effectively stopped. The universe is frozen, not in a state of ice, but in a state of perfect, unchanging equilibrium. It is a silent, static, and eternal calm. This is the ultimate triumph of the second law of thermodynamics. The universe, which began in a state of incredibly low entropy, a hot, dense, perfectly ordered point, has completed its long journey to the opposite extreme. All the usable energy has been spent, all the gradients have been flattened, and all the complexity has been erased. The story of the cosmos, with all its sound and fury, has concluded in a state of profound and everlasting silence. Is this, then, the end? Is this featureless void the final word in the cosmic story? For all intents and purposes, yes. Based on our current understanding of physics, this is the logical and ultimate conclusion. A universe that has simply run out of steam. It is a humbling and perhaps melancholic thought. The entire magnificent tapestry of cosmic history, the birth of galaxies, the forging of elements, the brief beautiful flame of life and consciousness, all ultimately dissolves into a cold, thin soup of nothingness. The universe will not remember us. It will not remember its own brilliant youth. All information, all history will be effectively erased. And yet, at the very edge of scientific understanding, where theory meets pure speculation, a few faint, tantalizing questions linger. Could there be a chapter after the end? Some theories, born from the strange world of quantum mechanics and cosmology, offer a glimmer of a possibility. One such idea is that of a quantum fluctuation, or quantum tunneling. In the bizarre rules of the quantum realm, it is not impossible for a new universe to spontaneously arise from the empty vacuum of the old one. Perhaps after an eternity in the dark era, a random fluctuation could create a new singularity, a new Big Bang, birthing a new cosmos with its own laws and its own destiny. The end would then not be an end, but a cosmic reset, the universe being reborn from its own ashes. Another, even more speculative idea is that of a cyclic universe. Some models propose that the state of maximum entropy could itself be unstable, triggering a collapse or a big crunch that leads to a new Big Bang. The universe would be like a cosmic lung, eternally breathing in and out, each cycle lasting an almost infinite amount of time. Our universe would be just one in an endless series of universes. These ideas are not mainstream science. They are philosophical and mathematical explorations at the very frontier of what we can imagine. They offer no certainty, only a question mark at the end of a definitive statement. But they speak to a deep human need to find cycles and renewal, even in the face of ultimate finality. Our journey so far has been one of cosmic solitude, charting the slow, inexorable decay of inanimate matter and energy. We have spoken of stars and black holes as if they were the only actors on this grand stage, but we have omitted the most remarkable phenomenon the universe has ever produced: life, and its even rarer descendant, intelligence. As the universe ages and cools, what will be the ultimate fate of consciousness? Can life, the universe's great rebellion against entropy, find a way to outlive the stars themselves? This question takes us from the realm of astrophysics into a space of speculative biology, engineering and philosophy. It is a story of survival on a scale that transcends all human experience. For any form of life to persist deep into the degenerate and black hole eras, it must solve a series of seemingly insurmountable challenges, the most fundamental of which is the problem of energy. In the stelliferous era, life is bathed in the abundant, high-quality energy of stars, but as the stars begin to die out, this energy source will dwindle and eventually vanish. An intelligent civilization, looking ahead, would understand that its survival depends on harvesting the remaining energy of the dying cosmos with ruthless efficiency. Their first grand project would be to capture the energy of the last shining stars. The concept of a Dyson sphere, or more realistically a Dyson swarm, becomes not a science fiction trope but a blueprint for survival. Civilizations would construct vast megastructures, swarms of orbiting collectors around the last stable red dwarf stars, capturing every last photon of their precious light. These final stellar oases would become the centers of civilization, islands of warmth and thought in an increasingly cold and dark universe. For trillions of years, these red dwarf stars would provide a steady, if dwindling, supply of power. Life would have to adapt to this low-energy existence. Biological processes would slow down. The frantic pace of life as we know it might give way to a slower, more deliberate form of existence. Perhaps civilizations would abandon their fragile biological bodies altogether, transitioning into more durable and energy-efficient forms. They might become beings of pure information, living within vast computational substrates powered by the dying light of their star. In this digital form, their perception of time could be altered. A subjective eternity could be experienced even as the universe outside grows old. But even the red dwarfs will not last forever. The day will come when the last one flickers and dies. The universe will then be truly dark. To survive past this point requires a new level of cosmic engineering. The only significant energy sources left will be the degenerate remnants of stars. A civilization could, in theory, harvest energy by feeding matter into a black hole. The accretion disk of a black hole, the swirling vortex of matter being torn apart before it crosses the event horizon, radiates immense amounts of energy. A sufficiently advanced civilization could carefully manage this process, treating the black hole as a cosmic power plant, dropping stellar remnants into its maw to generate the power needed to sustain their digital consciousness. Another possibility is to harness the rotational energy of a black hole through the Penrose process. A spinning black hole drags spacetime around with it, creating a region called the ergosphere. By dropping matter into this region and allowing it to split, a part of it can be ejected with more energy than it started with, effectively stealing energy from the black hole's spin. This is a source of power that could last for eons, long after the last stars have gone out. Life in this era would be a strange and ghostly existence. It would be a civilization clustered around a black hole, a silent, invisible god that is both its source of power and its ultimate doom. They would be the last survivors, living in a state of perpetual twilight, their thoughts and existence running on the energy of gravitational collapse. But even this cannot last. Eventually, all the available matter will have been consumed. The black holes themselves will begin to evaporate through Hawking radiation. Could even this process be harnessed? The radiation from an evaporating black hole is thermal, and where there is a temperature difference, energy can be extracted. A civilization could build a vast shell around an evaporating black hole to capture its faint warmth, using it to power their computations. However, the power output is minuscule, and it decreases as the black hole shrinks. This leads to the ultimate strategy for survival, the conservation of thought. As the available energy in the universe dwindles towards zero, any thinking being must become infinitely efficient. The physicist Freeman Dyson calculated that a civilization could, in theory, sustain consciousness forever in a cooling universe. The strategy is to have a finite number of thoughts, but to stretch them out over an infinite amount of time. The civilization would exist in a state of hibernation, activating for a brief period to have a single thought, powered by the universe's faint residual energy. It would then enter hibernation again for an ever longer period, waiting for the universe to cool further, which would allow the next thought to be processed with even less energy. In this scenario, subjective time for the civilization would continue indefinitely, even as objective, external time stretches towards infinity. Their existence would become a series of fleeting moments of consciousness separated by eons of frozen sleep. It is a cold, lonely, and minimalist form of immortality, a final, desperate flicker of thought in an otherwise dead cosmos. This vision forces us to ask what it truly means to be alive. Is an existence stretched so thin, with thoughts separated by trillions of years, still a meaningful one? It is a life stripped of all action, all interaction, all community. It is the life of a pure, disembodied mind clinging to existence by the thinnest possible thread. Ultimately, even this strategy may fail. The continued expansion of the universe, the possibility of proton decay, or some yet unknown physical law might make even this minimalist existence impossible. It seems that life, for all its ingenuity and resilience, cannot ultimately defeat the second law of thermodynamics. It can only postpone the inevitable. It can ride the wave of decreasing entropy, but it cannot stop the wave from eventually flattening onto the shore. The fate of intelligence, then, is perhaps the most tragic and heroic story in the entire cosmos. It is a story of a brief, brilliant flame of awareness that emerges in a universe destined for cold and darkness. It is a story of a struggle against impossible odds, a battle fought with physics and engineering on a cosmic scale, and it is a story that likely ends not with a bang, but with a final fading thought, a last flicker of consciousness before the universe settles into its final, eternal, and unthinking calm. The cosmos was born without a mind to witness it, and it will likely die without one as well. The brief interlude of consciousness is the most precious and fragile anomaly in its entire history. Our journey to the end of time has, until now, followed a single, lonely path, the path of the Big Freeze. It is a future of slow, inexorable decay, a universe that fades into a cold, dark, and empty expanse. This fate is dictated by the relentless expansion of space and the ironclad second law of thermodynamics. It is the most widely accepted scenario based on our current observations of the cosmos, but the universe may yet have a surprise in store. The story of the end is not yet written in stone, and there are other, more violent, and perhaps even more spectacular possibilities lurking in the equations of cosmology. To understand these alternative fates, we must consider the two great forces that govern the universe on a cosmic scale. On one side, there is the force of gravity, the universal attraction of all matter and energy. Gravity is the great sculptor, pulling things together, forming stars, galaxies, and clusters. It is a force that seeks to bind and collapse. On the other side, there is the mysterious force driving the expansion of the universe, a phenomenon known as dark energy. Dark energy is a repulsive force, an intrinsic property of space-time itself that pushes everything apart. The ultimate fate of the cosmos hangs in the balance of this epic tug-of-war between gravity and dark energy. The Big Freeze scenario assumes that dark energy is a cosmological constant, a gentle, unchanging pressure that causes the universe to expand at an ever-accelerating rate but not a violent one. But what if dark energy is not constant? What if its strength changes over time? This possibility opens the door to two other, very different endings. Let us first consider a future where gravity wins the war. This could happen if dark energy is not constant, but is instead a dynamic field that weakens over time, or even reverses its polarity and becomes attractive. In such a universe, the accelerating expansion we see today would eventually slow down. It would halt, and then it would reverse. This is the scenario known as the Big Crunch. After billions of years of expansion, the universe would reach a maximum size and then begin to contract. The galaxies, which have been rushing away from each other for eons, would reverse course and begin to hurtle towards one another. The cosmic clock would, in a sense, start to run backward. The sky, which had been growing darker and emptier, would slowly begin to fill with light again. At first, this process would be slow, almost imperceptible, but as the universe shrinks, the contraction would accelerate. Galaxies would begin to merge, not in the slow, graceful dance of the stelliferous era, but in a chaotic, violent demolition. The cosmic microwave background radiation, the faint afterglow of the Big Bang, would be blue-shifted to higher and higher energies. The background temperature of the universe would begin to rise. The universe would become a cosmic furnace. The rising background temperature would eventually become hotter than the surface of stars. Stars would be unable to radiate away their heat and would begin to cook from the outside in. Planets would be vaporized, their atmospheres stripped away. The universe would become a chaotic inferno of colliding stars and swirling superheated plasma. As the contraction continues, the temperature would become so high that atoms themselves would be torn apart, their electrons stripped from their nuclei. The universe would become a dense soup of elementary particles, much like it was in the moments after the Big Bang. Black holes would begin to merge, coalescing into a single universe-sized gigahole. In the final moments, the entire cosmos, all of space, time, matter, and energy, would collapse back into the same infinitesimal point from which it was born. It would be a fiery, cataclysmic end, the exact opposite of the cold, silent fade of the Big Freeze. The universe would be crushed out of existence in a final, infinitely hot and dense singularity. This idea leads to a tantalizing cyclical possibility. Could this Big Crunch singularity then bounce and trigger a new Big Bang, creating a new universe from the ashes of the old one? This is the idea of the cyclic universe, a cosmos that undergoes an eternal series of expansions and contractions, of big bangs and big crunches. Our universe would be just one iteration in an endless chain of cosmic death and rebirth. Now, let us consider the other extreme. What if dark energy is not constant but instead grows stronger over time? This hypothetical form of energy is known as phantom energy, and it leads to the most violent and terrifying fate of all, the Big Rip. In this scenario, the accelerating expansion of the universe becomes super-accelerated. The repulsive force of dark energy would grow so powerful that it would eventually overwhelm all other forces in the universe, including gravity itself. The consequences would be catastrophic, a systematic unbinding of the entire cosmos, from the largest structures to the smallest. The process would begin with the largest structures. A few billion years before the end, the repulsive force of phantom energy would become so strong that it would overcome the gravity holding galaxy clusters together. The great superclusters would be torn apart, their constituent galaxies flying off into the expanding void. A few 100 million years before the end, the force would be strong enough to overcome the gravity of individual galaxies. The Milky Way itself would be unbound. The stars, including our distant dead sun, would be ripped from their orbits and scattered, their majestic spiral structure dissolving into a chaotic, expanding cloud. About 3 months before the end, the force would overwhelm the gravity-holding solar systems together. Planets would be torn from their stars, sent hurtling into the darkness. In the final minutes, the end would become personal. The force would be strong enough to overcome the gravity of stars and planets themselves. The Earth, or what remains of it, would explode. The sun would be torn apart. With less than a second to go, the Big Rip would attack the very fabric of matter. The electromagnetic force holding atoms together would be overcome. Atoms would disintegrate into a spray of electrons and nuclei, and in the final, infinitesimal fraction of a second, around 10 to the power of minus 19 seconds, the phantom energy would become so powerful that it would overwhelm even the strong nuclear force, the the strongest force in nature. Atomic nuclei themselves would be ripped apart into their constituent protons and neutrons. And then, those particles too would be torn asunder. The universe would end not as a point, but as an infinitely vast expanse where every single particle is isolated from every other, with the space between them expanding at an infinite rate. The fabric of space-time itself would be torn apart. The story of the cosmos would end in a final, universal and instantaneous shredding of reality. These alternative endings, the fiery collapse of the Big Crunch and the violent tearing of the Big Rip, paint a very different picture from the calm, meditative fade of the Big Freeze. They remind us that the universe's ultimate destiny is not a settled question. It is one of the greatest unsolved mysteries in all of science, and the answer is hidden in the true nature of dark energy, a substance we are only just beginning to understand. The final chapter of the cosmos could be a slow fade, a fiery rebirth, or a violent end. The only certainty is that the universe, as we know it, will not last forever. Throughout our long and solitary journey, we have treated the universe as a single, all-encompassing entity. We have spoken of the Big Bang and the ultimate fate, as if our cosmos were the only story being told. But what if it is not? What if our entire universe, with its billions of galaxies and its grand unfolding destiny, is just one tiny, isolated bubble in an ocean of other universes? This is the breathtaking and deeply strange concept of the multiverse. This idea, which once belonged firmly to the realm of philosophy and fiction, has in recent decades found a foothold in theoretical physics. It emerges as a potential consequence of some of our most advanced theories, including string theory and cosmic inflation. It suggests that our universe is not unique. Instead, there may exist a vast, perhaps infinite ensemble of other universes, each potentially with its own unique physical laws, its own set of fundamental constants, and its own distinct history. The most compelling framework for this idea comes from the theory of eternal inflation. The theory of inflation proposes that in the first fraction of a second after the Big Bang, the universe underwent a period of hyper-accelerated expansion, growing from a subatomic size to a macroscopic scale almost instantaneously. This rapid stretching is what made the universe so vast and smooth. Eternal inflation takes this a step further. It suggests that this inflationary process, once started, never truly stops everywhere. Imagine the multiverse as a vast, eternally expanding ocean of inflationary energy. Within this ocean, pockets can randomly stop inflating and decay into a stable state, much like bubbles forming in boiling water. Each of these bubbles would be a new universe, born with its own Big Bang. Our entire observable universe, everything we can ever see or hope to see, would be just one such bubble in this immense cosmic foam. If this is true, it would represent the final and most profound emotion of our place in the cosmos. First, we learned that the Earth is not the centre of the solar system. Then, that our Sun is just one of billions of stars in a galaxy that is itself one of billions. Now, we are confronted with the possibility that our entire universe is just an insignificant bubble in an infinite multiverse. This concept radically reframes our understanding of our own existence. The physical laws and constants of our universe, which appear so perfectly fine-tuned to allow for the existence of stars, planets, and life, may not be special at all. In a multiverse, there would be countless other bubble universes with different laws. Most of these universes would be sterile and dead. Some might collapse back into a singularity moments after their birth. Others might expand so rapidly that no structures could ever form. Some might have different forces of nature, where chemistry as we know it would be impossible. Our universe, in this context, is simply one of the lucky bubbles, where the roll of the cosmic dice resulted in a set of laws hospitable to complexity and life. We exist here because we couldn't exist anywhere else. This is known as the anthropic principle. The universe appears fine-tuned for us because if it weren't, we wouldn't be here to observe it. The multiverse provides a natural explanation for this apparent fine-tuning, transforming it from a deep mystery into a simple matter of statistics. This idea also casts a new light on the ultimate fate of our cosmos. Whether our universe is destined for a big freeze, a big crunch, or a big rip, it is only the end of our particular bubble. The greater multiverse, the eternally inflating ocean, would continue to exist, constantly spawning new bubble universes. The end of our world would not be the end of everything, but merely the end of one isolated chapter in an infinite book. This raises a tantalizing, albeit highly speculative question. Could a sufficiently advanced civilization escape the death of its own universe? Could they find a way to puncture the wall of our spacetime bubble and cross the void into a younger, more hospitable universe? The challenges would be beyond anything we can currently imagine. The energy required to manipulate spacetime on this level would be colossal, and the space between the bubble universes, the eternally inflating bulk, would likely be a chaotic, high-energy realm where matter and information could not survive. A journey between universes would be less like a voyage across an ocean and more like a complete deconstruction and reconstruction of reality itself. Yet, for a civilization facing the ultimate end, the motivation would be absolute. Perhaps they could find a way to encode their information, their consciousness, their culture, their history, into a signal or a probe that could survive the journey and seed a new universe with their legacy. It would be the ultimate act of preservation, a message in a bottle thrown into the cosmic ocean. The multiverse concept also offers a different perspective on the beginning. If our universe was born from the multiverse, what came before our Big Bang? The question itself may be flawed, as time as we know it likely began with our universe. But in the context of the multiverse, our Big Bang was not a singular creation out of nothing, but simply a transition, one event in an ongoing eternal process of cosmic creation. This vision can be a source of profound calm and philosophical comfort. It suggests that the universe, or rather the multiverse, is a place of infinite possibility and endless renewal. Even as our own bubble fades into cold and darkness, new bubbles are being born, with new stars, new planets, and new chances for life to emerge. The creative engine of the cosmos is never truly exhausted. However, it is crucial to remember that the multiverse remains a theoretical concept. There is currently no direct observational evidence for the existence of other universes. They are, by their very nature, causally disconnected from us. We can never hope to see them or receive a signal from them. Their existence is inferred from the mathematics of our theories, not from empirical data. For this reason, some scientists and philosophers argue that the multiverse is not a scientific theory at all, but rather a metaphysical one, as it cannot be falsified. But whether it is ultimately proven true or not, the idea of the multiverse serves a valuable purpose. It pushes the boundaries of our imagination and forces us to question our most basic assumptions about reality. It is the logical conclusion of the Copernican principle, the idea that we are not in a special or privileged position. It suggests that the story of existence is far grander, far stranger, and far more vast than we ever dared to imagine. Our calm cosmos, our single, precious bubble of light and life, may be just one part of an infinite, silent, and majestic whole. And the end of our universe may not be the end of the story, but merely the turning of a single page in a book that has no beginning and no end. As we journey through the vast expanse of cosmic time and contemplate the grand, impersonal laws that govern the universe, a persistent and deeply unsettling question emerges. Why is the universe so perfectly suited for life? Why do the fundamental constants of nature, the strength of gravity, the charge of an electron, the mass of a proton, the energy of the vacuum, appear to be so exquisitely fine-tuned, as if on a knife's edge, to allow for the existence of stars, planets, chemistry, and ultimately us? If you were to alter any of these fundamental values by even a minuscule amount, the universe as we know it would not exist. If the strong nuclear force were just a few % weaker, atomic nuclei would not hold together, and the only element in the universe would be hydrogen. No stars, no planets, no life. If it were slightly stronger, stars would burn through their fuel so quickly that life would have no time to evolve. If gravity were a little stronger, the universe would have collapsed back on itself moments after the Big Bang. If it were weaker, galaxies and stars would never have formed. The list goes on and on. The universe appears to be balanced on an impossibly fine razor's edge. It's as if someone, or something, set the dials of reality with breathtaking precision to create a cosmos capable of hosting conscious observers. This puzzle is known as the fine-tuning problem, and it has led to one of the most controversial and thought-provoking ideas in all of science, the anthropic principle. The principle comes in several forms, but at its core it offers a simple, yet profound, resolution to the fine-tuning problem. The weak anthropic principle states that the observed values of the physical constants are what they are because if they were different, we would not be here to observe them. It turns the question on its head. We do not find ourselves in a life-friendly universe by sheer luck. We find ourselves here by necessity. We are, by definition, observers, and observation can only happen in a universe that allows observers to exist. Imagine a vast lottery with trillions upon trillions of tickets. The vast majority are losing tickets, but one single ticket is the winner. If you find yourself holding the winning ticket, you might be tempted to ask, why me? What are the odds? But the very fact that you are able to ask the question presupposes that you won. The losers cannot ponder their loss. Similarly, we can only find ourselves in a universe that won the cosmic lottery, a universe with the right combination of laws to produce us. The countless losing universes, sterile, empty, and lifeless, exist unobserved, their potential never realized. This line of reasoning naturally leads us back to the concept of the multiverse, which we explored in our previous chapter. The multiverse provides a physical mechanism for the weak anthropic principle. If there are countless bubble universes, each with its own randomly determined set of physical laws, then it is no longer a surprise that at least one of them, our own, would happen to have the right conditions for life. We are simply living in one of the habitable bubbles. The fine-tuning is not a miracle, it's a statistical inevitability. However, there is a more controversial and philosophically challenging version of this idea, the strong anthropic principle. This version goes a step further, suggesting that the universe must have had properties that allow life to develop within it at some stage in its history. This is not just a matter of observer selection, it implies a deeper, almost teleological principle at play. It hints that the universe is, in some fundamental way, compelled to give rise to consciousness. This idea is deeply unsettling for many scientists, as it seems to reintroduce a sense of purpose or design into the cosmos, concepts that science has long sought to move away from. It suggests that consciousness is not just a random, accidental byproduct of impersonal laws, but is somehow a fundamental and necessary part of the cosmic structure. Could it be that the universe exists in order to be observed? The physicist John Archibald Wheeler proposed a radical version of this, the participatory anthropic principle, which suggests that the universe does not even become fully real until it is observed by a conscious mind. In this view, observers are not just passive witnesses, they are active participants in creating the reality they perceive. This is a strange and dizzying thought. It would mean that the billions of years of cosmic history before the emergence of life were, in a sense, just a prelude, a potential reality waiting for a conscious mind to collapse its wave function and make it concrete. We would not be an accident of the universe, but its co-creators. Whether we accept the simple logic of the weak principle, or dare to contemplate the radical implications of the strong principle, the anthropic principle, forces us to confront our own existence in a new light. It challenges the idea that we are insignificant. While we may be physically small and our lives fleeting, our existence as conscious observers is tied to the most fundamental properties of the cosmos itself. The universe is calm and silent, but it is not necessarily random. There is an underlying mathematical elegance, a deep order that connects the microscopic world of particles to the macroscopic world of galaxies, and somehow allows for the bridge between them, us. The fine-tuning problem remains a frontier of scientific and philosophical inquiry. It could be a clue pointing towards the existence of a multiverse, a hint of a deeper law of nature we have yet to discover, or simply a limitation of our own understanding. But as we sit here, in this calm cosmos, able to ponder these questions, we are living proof of its extraordinary nature. The universe has produced a part of itself that can look back and wonder at the whole, and that, in itself, is the most profound observation of all. The fact that we can ask why is perhaps a more significant answer than any we could hope to find. In our grand cosmic narrative, from the fiery birth of the Big Bang to the cold, silent fade of the heat death, one silent character has been ever present, underpinning every event, every transformation, every moment of existence. That character is time. We experience it as a relentless, forward-flowing river, carrying us from a known past to an unknown future. But what is time? Is it a fundamental aspect of reality, or is it an emergent property, an illusion born of our own consciousness? And why does it seem to move in only one direction? This is the mystery of the arrow of time. At the most fundamental level of physics, the laws that govern reality, from Newton's laws of motion to Einstein's relativity and the equations of quantum mechanics, are, for the most part, time-symmetric. This means that the laws work just as well forwards in time as they do backwards. A video of two billiard balls colliding would look just as physically plausible if you played it in reverse. There is no inherent forwards direction written into the basic rules of the game. Yet, in our macroscopic world, time clearly has a powerful and undeniable direction. We see eggs break, but never unbreak. We see ice cubes melt, but never spontaneously form from a puddle of water. We remember the past, but we do not remember the future. This stark difference between the time-symmetric microscopic world and the timer-symmetric macroscopic world is the central puzzle of the arrow of time. The most powerful explanation for this phenomenon, as we have touched upon before, is the second law of thermodynamics. This law provides what is known as the thermodynamic arrow of time. It states that in any isolated system, entropy, a measure of disorder or randomness, always tends to increase. The universe as a whole is moving from a state of low entropy, high order, to a state of high entropy, high disorder. The forward direction of time that we experience is simply the direction of increasing entropy. The reason we see an egg break is because a broken egg is a much higher entropy state than a whole egg. There are vastly more ways for the molecules of an egg to be arranged in a splattered mess on the floor than there are for them to be perfectly arranged inside a shell. The universe, in its relentless search for more probable states, moves towards disorder. The past is simply the name we give to the time when the universe was in a more ordered, lower entropy state. The future is the direction of greater chaos. This explanation, however, raises an even deeper question. Why was the universe in such a state of incredibly low entropy to begin with? Why did the Big Bang produce a universe that was so perfectly ordered? This initial condition, this past hypothesis, is the ultimate source of the arrow of time. If the universe had been born in a state of high entropy, a chaotic uniform soup, then there would be no direction for entropy to increase, and consequently no arrow of time. Nothing would ever happen. The fact that the universe has a story at all is because it started with a highly improbable, perfectly ordered first page. Scientists do not yet have a complete answer for why the universe began this way. It remains one of the most profound mysteries in all of cosmology. Some theories suggest it might be related to the physics of the singularity itself, while others, like those involving a multiverse, suggest that our universe is just a rare, low-entropy fluctuation in a much larger high-entropy system. Regardless of the reason, this initial low-entropy state is the wound-up spring that has been powering the clock of the cosmos for nearly 14 billion years. This leads to another fascinating arrow of time, the psychological arrow of time. This is our subjective experience of time's passage, the feeling of moving from a fixed past to an open future. This psychological arrow is believed to be inextricably linked to the thermodynamic arrow. Our brains are physical systems that operate according to the laws of thermodynamics. To form a memory, our brain must perform a computation which consumes energy, low entropy, and dissipates heat, high entropy. In other words, the very act of creating a memory increases the entropy of the universe. Therefore, we can only form memories of the past, the direction in which entropy was lower. We cannot remember the future, because that would require the universe's entropy to decrease. Violation of the second law. Our sense of a fixed past and an open future is a direct consequence of the universe's thermodynamic journey. Let us now consider how the nature of time evolves as we travel into the deep future we have explored. In the stelliferous and degenerate eras, the arrow of time is strong. Stars are burning, matter is interacting, and entropy is robustly increasing. Events happen, and history unfolds. But as we enter the black hole era, things begin to change. The universe becomes vast, empty, and cold. The rate of entropy increase slows down dramatically. Events become incredibly rare, separated by unimaginable gulfs of time and space. The ticking of the cosmic clock becomes faint and almost imperceptible. Finally, in the dark era, after the last black hole has evaporated, the universe reaches a state of maximum entropy, or thermal equilibrium. It is a uniform, featureless sea of low-energy particles. In this state, there is no longer a thermodynamic arrow of time. There is no direction of increasing entropy, because entropy is already as high as it can be. What would time be like in such a universe? It is a question that pushes the limits of our understanding. With no events, no change, and no processes, would time still exist? Some physicists and philosophers argue that it would not. Time, they suggest, is not a fundamental backdrop to reality, but is rather an emergent property of change. If nothing happens, time ceases to have any meaning. The universe would be frozen in an eternal, timeless now. It would not be a state of waiting for something to happen, because the very concept of waiting or next would be meaningless. It would be a state of perfect, absolute stasis. However, even in this state of apparent nothingness, there is a final, ghostly possibility. According to quantum mechanics, even in a state of thermal equilibrium, there will always be random microscopic fluctuations. This is the concept of Poincaré recurrence. The Poincaré recurrence theorem states that in any closed system, given a long enough period of time, it will eventually return to a state arbitrarily close to its initial state. Applied to the entire universe, this idea is staggering. It suggests that if you wait long enough, a timescale so vast it makes the Google year lifespan of a black hole seem like an instant, the random fluctuations of the particles in the empty void could, by pure chance, conspire to recreate a state of lower entropy. A star could fluctuate into existence, a planet could form, a brain could spontaneously assemble from the void, complete with a full set of memories of a life it never lived, a Boltzmann brain. Even more astonishingly, given a truly infinite amount of time, it is not just possible but statistically inevitable that a fluctuation could occur that is so large it recreates our entire observable universe, or even triggers a new Big Bang. The arrow of time could spontaneously re-emerge from the chaos. The cosmic clock, after an eternity of stillness, could start ticking again. This is perhaps the strangest and most profound idea about the nature of time. It suggests that even in the face of the heat death, the story may not be truly over. The universe might be a place of infinite, random renewals. However, a universe born from such a fluctuation would be a lonely and terrifying place. It would be a momentary island of order in an infinite ocean of chaos, with no history leading up to it and no future beyond its inevitable dissolution back into the void. Our perception of time, therefore, is a precious gift of our universe's specific, low-entropy beginning. We live in the unfolding narrative, the coherent story that started with the Big Bang. We are not random fluctuations, but the products of a long, unbroken chain of cause and effect, of increasing complexity and evolving order, all driven by the relentless forward march of the thermodynamic arrow of time. Time, for us, is the canvas on which the entire story of the calm cosmos is painted, and the fact that this canvas has a direction is the reason there is a story to tell at all. Throughout our cosmic chronicle, we have spoken of space as the stage and time as the script. We have envisioned a universe where objects move through space and events unfold in time. But what if this perception is incomplete? What if space and time are not separate entities, but are instead two sides of the same coin, woven together into a single, dynamic fabric? This is the revolutionary idea at the heart of Albert Einstein's theory of general relativity, and it fundamentally reshaped our understanding of the universe. This single, unified entity is called spacetime. Before Einstein, the universe was understood through the lens of Isaac Newton. In the Newtonian view, space was a fixed, absolute and unchanging backdrop, a sort of invisible grid upon which the cosmic drama played out. Time was also absolute, a universal clock that ticked at the same rate for everyone, everywhere. Gravity in this picture was a mysterious, instantaneous force, an invisible tether that reached across the vastness of space, pulling objects toward one another. While Newton's laws were incredibly successful at describing the motion of planets and predicting tides, they left a deep question unanswered. How did gravity actually work? How did the sun, millions of miles away, tell the Earth to stay in its orbit? Einstein's genius was to propose a completely new answer. He suggested that gravity is not a force at all. Instead, gravity is a consequence of the curvature of spacetime. He asked us to imagine spacetime as a flexible, four-dimensional fabric. The presence of mass and energy warps or curves this fabric, much like a heavy bowling ball placed on a stretched rubber sheet. Massive objects create deep wells in spacetime. Other objects, like planets, are not being pulled by a force. They are simply following the straightest possible path through this curved space-time. An orbit, in this view, is the natural straight-line motion of an object rolling along the curved edge of the gravitational well created by a star. This is a profound shift in perspective. Gravity is no longer a mysterious force acting at a distance. It is the geometry of the cosmos itself. Matter tells space-time how to curve, and curved space-time tells matter how to move. This elegant dance is the essence of general relativity. This theory also revealed the intimate connection between space and time. Einstein showed that the faster you move through space, the slower you move through time relative to a stationary observer. This is the phenomenon of time dilation. It means there is no universal clock. Time is relative. It depends on your motion and your gravitational environment. For astronauts aboard the International Space Station, time ticks just a fraction of a second slower than it does for us on Earth, both because of their high speed and because they are in a slightly weaker gravitational field. For an object falling into a black hole, this effect becomes extreme. To an outside observer, the object would appear to slow down as it approaches the event horizon, its clock ticking ever slower until it seems to freeze in time, its light red-shifted into oblivion. The concept of space-time as a dynamic fabric allows us to understand the most extreme phenomena in our cosmic story. A black hole is a region where a massive object has curved space-time so intensely that it has created a hole with no bottom. The event horizon is the point where the curvature becomes so steep that the path forward for everything, including light, inevitably leads to the central singularity. It is not a prison made of matter, but a prison made of pure geometry. Similarly, the Big Bang can be understood not as an explosion in space, but as the expansion of space-time itself. The initial singularity was a point of infinite curvature and density. The Big Bang was the moment this space-time fabric began to unfurl and expand, carrying all the matter and energy with it. The galaxy is not flying apart through a pre-existing empty space. Rather, the space between them is being created and stretched, causing them to move apart. This is why the expansion of the universe is not limited by the speed of light. It is the fabric of reality itself that is expanding. Even the gravitational waves we discussed in the degenerate era are a direct prediction of this theory. When massive objects like black holes or neutron stars collide, they create ripples in the space-time fabric, much like two colliding boats create waves in a pond. These ripples travel outwards at the speed of a light, carrying with them information about the cataclysmic event that created them. The first direct detection of these waves in 2015 was a monumental achievement, opening a new window onto the universe. It was the first time we had heard the sound of space-time itself ringing. Now, let us consider the role of space-time in the ultimate fate of the cosmos. In the Big Freeze scenario, the expansion of space-time driven by dark energy continues forever. The fabric of the cosmos becomes stretched ever thinner, becoming colder, darker, and flatter. The curvature created by matter becomes insignificant as the matter itself disperses. The universe evolves into a vast, featureless, and geometrically simple expanse. In the Big Crunch scenario, the geometry tells a different story. The expansion halts, and the space-time fabric begins to collapse in on itself. The curvature grows, becoming more and more extreme, until all of reality converges into a final singularity, a point of infinite curvature, where the laws of physics and the concept of space-time itself break down. And in the most violent end, the Big Rip, the story is one of space-time tearing itself apart. The repulsive force of phantom energy becomes so strong that it causes the expansion of the space-time fabric to accelerate infinitely. This is not just a stretching, but a violent shredding. The very geometry of existence would unravel, leading to a final state of infinite separation and infinite expansion, where the concept of distance itself loses meaning. Space-time, therefore, is not just the setting of our story. It is a central character. It is a dynamic, evolving entity that dictates the motion of stars, governs the expansion of the cosmos, and ultimately shapes its own destiny. It is the invisible architecture of reality, the underlying fabric upon which the entire history of the calm cosmos, from its first fiery moment to its last silent breath, is woven. Understanding this fabric is to understand the fundamental language in which the universe is written. It is the calm geometric foundation of all existence. Our exploration of the cosmos has so far focused on the familiar: the brilliant light of stars, the swirling dust of nebulae, the dense matter of planets, and the fundamental particles that form the building blocks of everything we can see and touch. We have built a grand narrative based on this visible universe. But what if this entire story, this entire cosmic drama, is just a sideshow? What if the universe we know, the one made of atoms, the one that shines, accounts for less than 5% of what is actually out there? This is the humbling and profound reality of modern cosmology. The vast majority of the universe is hidden from us, residing in a dark sector that does not emit, reflect, or interact with light in any way. This hidden universe is dominated by two enigmatic substances: dark matter and dark energy. Let us first delve into the mystery of dark matter. The story of its discovery begins in the 1930s with the astronomer Fritz Zwicky, who was observing the Coma cluster of galaxies. He noticed something deeply strange. The galaxies within the cluster were moving far too quickly. Based on the amount of visible matter, the stars and gas he could see, the gravitational pull should have been far too weak to hold the cluster together. The galaxies should have flown apart, dissipating into the void. It was as if some unseen, invisible mass was providing the extra gravitational glue needed to bind the cluster. Zwicky called this missing mass dunkle Materie, or dark matter. For decades his observations were largely ignored, but in the 1970s the astronomer Vera Rubin provided undeniable evidence that solidified the case. She was studying the rotation of individual spiral galaxies, like our own Milky Way. According to Newtonian physics, the stars at the outer edges of a galaxy should orbit much more slowly than the stars closer to the centre, just as the outer planets in our solar system move more slowly than the inner ones. But this is not what Rubin found. She discovered that the stars at the outer edges were moving just as fast, if not faster, than the stars near the centre. This flat rotation curve was inexplicable unless there was a massive invisible halo of matter surrounding the entire galaxy, extending far beyond the visible disk of stars. This was the smoking gun. The only way to explain these observations was to posit the existence of a new kind of matter, a substance that does not interact with light, hence dark, but which does exert a powerful gravitational pull. Since then, evidence for dark matter has poured in from every corner of cosmology. We see its effects in gravitational lensing, where the gravity of massive, invisible clumps of dark matter bends the light from distant galaxies, distorting their images. We see its imprint on the cosmic microwave background, the afterglow of the Big Bang, where its gravitational influence shaped the initial seeds of cosmic structure. Today, the scientific consensus is that dark matter makes up about 27% of the total mass-energy content of the universe, outnumbering ordinary matter by a factor of more than 5 to 1. But what is it? This remains one of the biggest unsolved questions in all of science. We know what it is not. It is not just faint stars or cold gas clouds, as we would be able to detect those in other ways. It is not ordinary matter in any form we know. It must be something entirely new, a particle that is not part of the standard model of particle physics. The leading candidates are hypothetical particles known as WIMPs, weakly interacting massive particles. These particles, as their name suggests, would be massive, providing the gravitational pull, but would interact with ordinary matter only through the weak nuclear force and gravity, making them incredibly difficult to detect. All over the world, scientists are running highly sensitive experiments deep underground, shielded from cosmic rays, hoping to catch the faint signal of a single WIMP particle bumping into an atomic nucleus. Other candidates include sterile neutrinos or even stranger particles called axions. Despite decades of searching, we have not yet found a definitive particle of dark matter. Dark matter is the silent architect of the cosmos. In the early universe, it was the gravitational scaffolding upon which all structure was built. While ordinary matter was being pushed around by the pressure of light, dark matter, being immune to light, could begin to clump together much earlier. It formed vast, invisible halos, the gravitational wells into which ordinary matter later fell, eventually forming the galaxies we see today. Without dark matter, there would be no galaxies, no stars, and no us. We are living in a universe that was built by a substance we cannot see and do not understand. Now, let us turn to the even more mysterious and dominant component of the cosmos, dark energy. If dark matter is the invisible glue holding things together, dark energy is the invisible force pushing everything apart. As we discussed, observations in the late 1990s revealed that the expansion of the universe is not slowing down, as was expected due to gravity, but is actually accelerating. This was a shocking discovery that completely overturned our understanding of the universe's ultimate fate. To explain this cosmic acceleration, physicists proposed the existence of a new form of energy, a repulsive force that is an intrinsic property of spacetime itself. This is dark energy. It acts like a form of anti-gravity pushing space apart, and its influence is immense. According to our best measurements, dark energy accounts for a staggering 68% of the total energy density of the universe. This means that the universe we know, the atoms, the stars, the galaxies, and even the mysterious dark matter, collectively make up less than a third of the cosmos. The vast majority of the universe is composed of this strange, repulsive energy that is driving its runaway expansion. What is dark energy? The truth is, we have even less of an idea than we do about dark matter. The leading hypothesis is that it is the cosmological constant, a concept Einstein himself proposed and later called his biggest blunder. It represents the energy of the vacuum itself, the baseline energy of empty space. Quantum physics predicts that empty space should be filled with a seething sea of virtual particles, giving it an inherent energy. The problem is that when physicists try to calculate the theoretical value of this vacuum energy, the number they get is absurdly large, 10 to the power of 120 times larger than what we observe. This discrepancy, known as the cosmological constant problem, is one of the most profound and embarrassing failures in the history of physics. Another possibility is that dark energy is not a constant but a dynamic field that can change over time, which we previously referred to as quintessence, or phantom energy. This would mean that the future of the universe is even more uncertain, potentially leading to the dramatic fates of the Big Rip or a future Big Crunch. The existence of dark matter and dark energy forces us to confront a humbling reality. The universe is not what it seems. The cosmos we see, the one we have been charting on our journey, is just the foam on the surface of a deep, dark ocean. The fundamental nature of 95% of our universe remains a complete mystery. These two dark components are the primary drivers of the universe's past, present, and future. Dark matter built the structures, and dark energy will determine their ultimate fate. Our calm cosmos is therefore a hidden cosmos. Its true nature is veiled from us, its destiny dictated by invisible forces we're only just beginning to perceive. The quest to understand dark matter and dark energy is the foremost challenge of 21st century cosmology. It is a search that will require new theories, new experiments, and perhaps a complete revolution in our understanding of physics. Until we solve these mysteries, any story we tell about the universe will remain beautifully, tantalizingly, and profoundly incomplete. In our quest to understand the cosmos, we are like cosmic archaeologists, sifting through the layers of time to piece together the story of our universe. Our most powerful tool in this endeavor is light. The farther we look out into space, the further back in time we see, because the light from distant objects has taken billions of years to reach us. We can see galaxies as they were when the universe was just a fraction of its current age. But there is a limit to how far back we can look with conventional telescopes. There is a wall, a curtain of fire beyond which the universe was opaque, and the faint fading glow of that ancient fire is the most important and informative signal in all of cosmology. It is the cosmic microwave background, or the CMB. To understand the CMB, we must journey back to the early universe, to a time approximately 380,000 years after the Big Bang. The universe before this point was a profoundly different place. It was an incredibly hot, dense, and seething inferno of fundamental particles. It was so hot that atoms as we know them could not exist. Electrons, instead of orbiting atomic nuclei, were ripped away, forming a dense ionized soup of charged particles called a plasma. In this plasma state, the universe was completely opaque. Photons, the particles of light, could not travel freely. They were constantly scattering off the free-floating electrons like pinballs in a dense, chaotic machine. A photon would travel a short distance, collide with an electron, get absorbed and re-emitted in a random direction, only to collide with another electron moments later. The entire universe was a glowing, impenetrable fog. If you could have existed there, you would have seen a brilliant, uniform white light in every direction, like being inside the sun. However, the universe was expanding, and as it expanded, it cooled. Over 380,000 years, the temperature dropped to a critical threshold of about 3,000 Kelvin. At this temperature, it was finally cool enough for the protons and electrons to combine and form the first stable, neutral atoms of hydrogen and helium. This event is known as recombination. The moment of recombination was a pivotal turning point in cosmic history. With the free electrons now bound up inside atoms, the primary obstacle for photons was removed. The universe suddenly and dramatically became transparent. The photons that were present at that exact moment were decoupled from matter and were finally free to travel unimpeded through the cosmos. This first light has been travelling across the universe ever since. For nearly 13.8 billion years, this ancient light is what we now detect as the cosmic microwave background. When this light was first released, it was as brilliant as the surface of a star. But over the subsequent eons, as the universe has expanded, the fabric of space-time itself has stretched, and this light has been stretched along with it. Its wavelength has been elongated from high-energy visible light into the low-energy microwave part of the electromagnetic spectrum. Its temperature has dropped from 3,000 Kelvin to a mere 2.725 Kelvin, just a few degrees above absolute zero. Today, the CMB is a faint, cold, and almost perfectly uniform glow of microwave radiation that bathes the entire sky, coming from every direction, with no apparent source. It is the oldest light in the universe, the faint, fading echo of the Big Bang's initial fireball. The discovery of the CMB in 1965 by Arno Penzias and Robert Wilson was a landmark moment in science. They were radio astronomers trying to eliminate a persistent faint hiss of background noise in their antenna. No matter where they pointed it, the noise remained. They soon realized they had stumbled upon the afterglow of creation itself. This discovery provided the single most powerful piece of evidence for the Big Bang theory, transforming it from a speculative hypothesis into the cornerstone of modern cosmology. At first glance, the CMB appears to be perfectly uniform, with the same temperature in every direction. This uniformity is itself a crucial piece of evidence, telling us that the early universe was incredibly smooth and well mixed. However, in the 1990s, NASA's COBE satellite and later the WMAP and Planck missions made an even more profound discovery. They found that the CMB is not perfectly uniform after all. It contains tiny, almost imperceptible temperature fluctuations, variations of just 1 part in 100,000. These tiny ripples, these minuscule hot and cold spots in the ancient fire, are the seeds of all structure in the universe today. They are the imprints of quantum fluctuations from the first fraction of a second of the universe's existence, magnified to cosmic scales by the process of inflation. The slightly denser, slightly hotter regions were the areas where gravity had a slightly stronger grip. Over billions of years, these regions would attract more and more matter, both dark and ordinary, eventually collapsing to form the first stars, the first galaxies, and the vast cosmic web of clusters and superclusters we see today. The colder, less dense regions would become the great cosmic voids. When we look at a map of the CMB, we're looking at a baby picture of the universe. We're seeing the blueprint for the entire cosmos. By studying the precise pattern, size, and distribution of these fluctuations, cosmologists can extract an incredible amount of information about the fundamental properties of our universe. The CMB tells us the age of the universe, its geometry, it is almost perfectly flat, and its composition. It is from the detailed analysis of the CMB that we derive our best estimates for the amounts of ordinary matter, 4.9%, dark matter, 26.8%, and dark energy, 68.3%. The CMB is a time machine, a cosmic Rosetta Stone. It allows us to test our theories about the very first moments of creation and to understand the physical processes that have shaped the universe's evolution. It is a testament to the power of scientific inquiry that we can detect and analyze the faint 13.8 billion-year-old echo of the Big Bang with such astonishing precision. This ancient light, This calm, cold glow that fills the cosmos is the most profound connection we have to our own origins. It is a silent reminder that the entire vast and complex universe we see around us, every star, every planet, every living being, emerged from these tiny simple ripples in a primordial sea of fire. It is the foundation of our cosmic story, the first chapter, written in a faint microwave light across the entire canvas of the sky. In the grand cosmic theatre, there are no villains or heroes, only the impersonal forces of nature playing out their roles. But if there were a character that commanded both ultimate authority and profound mystery, it would be the black hole. A black hole is not just a dense object. It is the logical and terrifying conclusion of gravity's relentless nature. It is a point of no return, a tear in the fabric of reality, and a place where the laws of physics as we know them are crushed into oblivion. It is gravity's ultimate, undisputed triumph. The concept of an object so massive that even light could not escape dates back to the 18th century, but it was Einstein's theory of general relativity that gave us the modern framework to understand them. As we've discussed, gravity is the curvature of space-time caused by mass and energy. A black hole is what happens when an immense amount of mass is concentrated into an incredibly small volume, causing space-time to curve so extremely that it effectively closes in on itself. The surface of a black hole is called the event horizon. This is not a physical barrier, but an informational one. It is the point of no return. Once an object or a ray of light crosses the event horizon, it is irrevocably trapped. The escape velocity required to leave the black hole's gravitational pull exceeds the speed of light, and since nothing can travel faster than light, escape is impossible. The event horizon is a one-way door in the cosmos. At the very centre of the black hole lies the singularity. This is the point where all the mass that has fallen into the black hole is crushed into a region of zero volume and infinite density. At the singularity, the curvature of space-time becomes infinite, and our current laws of physics, including general relativity itself, break down completely. We do not yet have a theory of quantum gravity that can describe what happens at this point. The singularity represents a fundamental limit to our current knowledge, a place where the universe hides its deepest secrets. Black holes come in a variety of sizes, each formed through different cosmic processes. The most common are stellar mass black holes. These are formed from the death of a single massive star. When a star more than about 20 times the mass of our Sun exhausts its nuclear fuel, it can no longer support itself against the inward crush of its own gravity. The core collapses catastrophically, triggering a massive supernova explosion that blasts the star's outer layers into space. The remaining core, however, continues to collapse indefinitely, with no force in nature strong enough to halt it. It collapses past the density of a white dwarf, past the density of a neutron star, and keeps going until it forms a singularity, cloaked by an event horizon. Our Milky Way galaxy is estimated to contain at least 100 million of these stellar mass black holes, silently drifting through the darkness. On the other end of the scale are the supermassive black holes, SMBHAs. These are the colossal titans of the cosmos, with masses ranging from millions to billions of times that of our Sun. We have found compelling evidence that one of these giants lurks at the centre of nearly every large galaxy, including our own. At the heart of the Milky Way lies Sagittarius, a star, pronounced a star, a supermassive black hole with a mass of about 4 million suns. The origin of SMBHS is still an active area of research. They may have formed from the collapse of the very first gigantic stars, or from the direct collapse of massive gas clouds in the early universe, and then grew over billions of years by consuming stars, gas, and even merging with other black holes. The influence of a black hole extends far beyond its event horizon. The immense gravity creates an extreme and violent environment. As gas, dust, and stars are pulled towards the black hole, they don't fall straight in. Instead, they are whipped into a swirling, flattened vortex called an accretion disk. The material in this disk orbits the black hole at incredible speeds, close to the speed of light. The friction and compression within the disk heat the material to millions of degrees, causing it to glow intensely across the electromagnetic spectrum, from radio waves to X-rays. It is this brilliantly glowing accretion disk, not the black hole itself, that allows us to detect and study these objects. Paradoxically, the regions around black holes are some of the brightest and most energetic places in the entire universe. Via supermassive black holes, the magnetic fields in the accretion disk can become twisted into powerful funnels. These funnels can capture some of the infalling material and launch it outwards in two colossal focused beams of particles and radiation that travel at nearly the speed of light. These are known as relativistic jets. These jets can be immense, stretching for hundreds of thousands of light years, far beyond the boundaries of their host galaxy. When a galaxy has a bright accretion disk and powerful jets, it is called an active galactic nucleus, or a quasar. Quasars are the most luminous objects in the universe, beacons of light visible from across cosmic time, all powered by the gravitational energy of a feeding supermassive black hole. The effects of a black hole on time are just as profound. As predicted by general relativity, time slows down in a strong gravitational field. This gravitational time dilation means that for an observer falling towards a black hole, their clock would tick slower and slower relative to a distant observer. To the distant observer, the falling person would appear to move in slow motion, their image becoming redder and dimmer as they approach the event horizon, until they seem to freeze and fade away completely, never quite crossing the boundary. The falling person, however, would experience no such thing. In their own frame of reference, their clock would tick normally, and they would cross the event horizon in a finite amount of time, unaware of the moment they pass the point of no return. Inside the event horizon, the nature of space and time is warped in a bizarre way. The direction towards the singularity becomes as inevitable as the future is for us outside. Just as we are always moving forward in time, an object inside a black hole is always moving towards the singularity. The singularity is no longer a place in space, but a moment in the future, a future that cannot be avoided. Black holes are not just cosmic vacuum cleaners, they are fundamental engines of cosmic evolution. They regulate the growth of galaxies, their powerful jets can clear out gas and quench star formation, and their mergers are the most powerful sources of gravitational waves in the universe. They are the ultimate expression of gravity's power, objects that bend space, warp time, and challenge the very limits of our understanding. They are the calm, dark, and silent hearts around which the luminous universe revolves. Our exploration of the cosmos has so far focused on the familiar: the brilliant light of stars, the swirling dust of nebulae, the dense matter of planets, and the fundamental particles that form the building blocks of everything we can see and touch. We have built a grand narrative based on this visible universe. But what if this entire story, this entire cosmic drama, is just a sideshow? What if the universe we know, the one made of atoms, the one that shines, accounts for less than 5% of what is actually out there? This is the humbling and profound reality of modern cosmology. The vast majority of the universe is hidden from us, residing in a dark sector that does not emit, reflect, or interact with light in any way. This hidden universe is dominated by two enigmatic substances: dark matter and dark energy. Let us first delve into the mystery of dark matter. The story of its discovery begins in the 1930s with the astronomer Fritz Zwicky, who was observing the Coma cluster of galaxies. He noticed something deeply strange. The galaxies within the cluster were moving far too quickly. Based on the amount of visible matter the stars and gas he could see, the gravitational pull should have been far too weak to hold the cluster together. The galaxies should have flown apart, dissipating into the void. It was as if some unseen, invisible mass was providing the extra gravitational glue needed to bind the cluster. Zwicky called this missing mass dunkle Materie, or dark matter. For decades, his observations were largely ignored, but in the 1970s, the astronomer Vera Rubin provided undeniable evidence that solidified the case. She was studying the rotation of individual spiral galaxies, like our own Milky Way. According to Newtonian physics, the stars at the outer edges of a galaxy should orbit much more slowly than the stars closer to the centre, just as the outer planets in our solar system move more slowly than the inner ones. But this is not what Rubin found. She discovered that the stars at the outer edges were moving just as fast, if not faster, than the stars near the centre. This flat rotation curve was inexplicable unless there was a massive invisible halo of matter surrounding the entire galaxy, extending far beyond the visible disk of stars. This was the smoking gun. The only way to explain these observations was to posit the existence of a new kind of matter, a substance that does not interact with light, hence dark, but which does exert a powerful gravitational pull. Since then, evidence for dark matter has poured in from every corner of cosmology. We see its effects in gravitational lensing, where the gravity of massive, invisible clumps of dark matter bends the light from distant galaxies, distorting their images. We see its imprint on the cosmic microwave background, the afterglow of the Big Bang, where its gravitational influence shaped the initial seeds of cosmic structure. Today, the scientific consensus is that dark matter makes up about 27% of the total mass energy content of the universe, outnumbering ordinary matter by a factor of more than 5 to 1. But what is it? This remains one of the biggest unsolved questions in all of science. We know what it is not. It is not just faint stars or cold gas clouds, as we would be able to detect those in other ways. It is not ordinary matter in any form we know. It must be something entirely new, a particle that is not part of the standard model of particle physics. The leading candidates are hypothetical particles known as WIMPs, weakly interacting massive particles. These particles, as their name suggests, would be massive, providing the gravitational pull, but would interact with ordinary matter only through the weak nuclear force and gravity, making them incredibly difficult to detect. All over the world, scientists are running highly sensitive experiments deep underground, shielded from cosmic rays, hoping to catch the faint signal of a single WIMP particle, bumping into an atomic nucleus. Other candidates include sterile neutrinos, or even stranger particles called axions. Despite decades of searching, we have not yet found a definitive particle of dark matter. Dark matter is the silent architect of the cosmos. In the early universe, it was the gravitational scaffolding upon which all structure was built. While ordinary matter was being pushed around by the pressure of light, dark matter, being immune to light, could begin to clump together much earlier. It formed vast, invisible halos, the gravitational wells into which ordinary matter later fell, eventually forming the galaxies we see today. Without dark matter, there would be no galaxies, no stars, and no us. We are living in a universe that was built by a substance we cannot see and do not understand. Now, let us turn to the even more mysterious and dominant component of the cosmos, dark energy. If dark matter is the invisible glue holding things together, dark energy is the invisible force pushing everything apart. As we discussed, observations in the late 1990s revealed that the expansion of the universe is not slowing down, as was expected due to gravity, but is actually accelerating. This was a shocking discovery that completely overturned our understanding of the universe's ultimate fate. To explain this cosmic acceleration, physicists proposed the existence of a new form of energy, a repulsive force that is an intrinsic property of spacetime itself. This is dark energy. It acts like a form of anti-gravity, pushing space apart, and its influence is immense. According to our best measurements, dark energy accounts for a staggering 68% of the total energy density of the universe. This means that the universe we know, the atoms, the stars, the galaxies, and even the mysterious dark matter, collectively make up less than a third of the cosmos. The vast majority of the universe is composed of this strange, repulsive energy that is driving its runaway expansion. What is dark energy? The truth is, we have even less of an idea than we do about dark matter. The leading hypothesis is that it is the cosmological constant, a concept Einstein himself proposed and later called his biggest blunder. It represents the energy of the vacuum itself, the baseline energy of empty space. Quantum physics predicts that empty space should be filled with a seething sea of virtual particles, giving it an inherent energy. The problem is that when physicists try to calculate the theoretical value of this vacuum energy, the number they get is absurdly large. 10 to the power of 120 times larger than what we observe. This discrepancy, known as the cosmological constant problem, is one of the most profound and embarrassing failures in the history of physics. Another possibility is that dark energy is not a constant, but a dynamic field that can change over time, which we previously referred to as quintessence, or phantom energy. This would mean that the future of the universe is even more uncertain, potentially leading to the dramatic fates of the Big Rip or a future Big Crunch. The existence of dark matter and dark energy forces us to confront a humbling reality. The universe is not what it seems. The cosmos we see, the one we have been charting on our journey, is just the foam on the surface of a deep, dark ocean. The fundamental nature of 95% of our universe remains a complete mystery. These two dark components are the primary drivers of the universe's past, present, and future. Dark matter built the structures, and dark energy will determine their ultimate fate. Our calm cosmos is, therefore, a hidden cosmos. Its true nature is veiled from us, its destiny dictated by invisible forces we're only just beginning to perceive. The quest to understand dark matter and dark energy is the foremost challenge of 21st century cosmology. It is a search that will require new theories, new experiments, and perhaps a complete revolution in our understanding of physics. Until we solve these mysteries, any story we tell about the universe will remain beautifully, tantalizingly, and profoundly incomplete. Our cosmic journey has taken us through the vastness of space and the abyss of time, exploring galaxies, stars, and the enigmatic nature of black holes. Now, we must undertake a journey in the opposite direction. We must shrink down, past the scale of planets, past the size of atoms, deep into the subatomic realm, to understand the fundamental ingredients from which everything is made. This is the world of particle physics, and its crowning achievement is a theory of breathtaking elegance and predictive power, the Standard Model. The Standard Model of particle physics is, to date, humanity's most successful and rigorously tested theory about the fundamental nature of reality. It is a theory of almost everything. It describes, with astonishing precision, all the known fundamental particles that make up matter and all the fundamental forces that govern their interactions, with the notable exception of gravity. It is the rulebook for the cosmic game, the cast of characters and the list of actions they can perform. To understand the Standard Model is to understand the alphabet in which the story of the universe is written. The model organizes the fundamental particles into two main families: fermions, which are the particles of matter, and bosons, which are the particles that carry forces. Let's first meet the fermions, the building blocks of substance. These are the particles that have mass and make up everything we can touch. The fermions themselves are divided into two groups: quarks and leptons. Quarks are sociable, but peculiar particles. They are never found alone in nature. They always exist bound together in groups to form composite particles, like the protons and neutrons that make up the nucleus of every atom. There are 6 flavors of quarks, organized into 3 generations of increasing mass. First generation, the up quark and the down quark. These are the most common and stable quarks. One proton is made of 2 up quarks and 1 down quark, while a neutron is made of 1 up quark and 2 down quarks. All the ordinary matter of our daily lives, every chair, every planet, every star, is ultimately made from just these 2 types of quarks, along with electrons. Second generation, the charm quark and the strange quark. These are more massive and less stable versions of the first generation. They were common in the high-energy environment of the early universe, but now only appear fleetingly in high-energy particle collisions in cosmic rays or particle accelerators. Third generation, the top quark and the bottom quark. These are the heavyweights of the quark family. The top quark is the most massive fundamental particle ever discovered, with a mass similar to that of a gold atom. Like the second generation, these particles are highly unstable and decay almost instantly into lighter particles. The second group of fermions are the leptons. Unlike quarks, leptons are solitary particles that can exist on their own. The most famous lepton is the electron, the tiny, negatively charged particle that orbits the atomic nucleus and is responsible for all of chemistry and electricity. Like the quarks, leptons also come in 3 generations. First generation, the electron and the electron neutrino. Neutrinos are incredibly strange particles. They are almost massless, have no electric charge, and interact so weakly with other matter that trillions of them are passing through your body every second without you ever noticing. They are the ghosts of the particle world. Second and third generations. These consist of heavier, unstable cousins of the electron, the muon and the tau, each with its own corresponding neutrino, the muon neutrino and the tau neutrino. This collection of 12 fermions, 6 quarks and 6 leptons, constitutes the complete roster of matter particles in the Standard Model. It is a remarkably simple and elegant picture. Everything tangible in the universe is made from combinations of these 12 fundamental ingredients, but these particles would be nothing without the forces that govern their interactions. This is where the bosons come in. The Standard Model describes 3 of the 4 fundamental forces of nature, and for each force, there is a corresponding force-carrying particle, or boson. 1. The strong nuclear force. This is the strongest of all the forces, but it acts only over incredibly short distances, within the nucleus of an atom. It is the force that glues quarks together to form protons and neutrons, and it also binds protons and neutrons together to form the atomic nucleus, overcoming the immense electrical repulsion between the positively charged protons. The boson that carries the strong force is called the gluon. 2. The weak nuclear force. This force is responsible for radioactive decay. It is the only force that can change the flavour of a quark or a lepton. For example, it allows a neutron to decay into a proton, an electron, and a neutrino. This process is fundamental to the nuclear reactions that power the Sun. The weak force is carried by 2 types of bosons, the massive W and Z bosons. 3. The electromagnetic force. This force governs the interactions between electrically charged particles. It is responsible for almost all the phenomena we experience in our daily lives: light, electricity, magnetism, and the structure of atoms and molecules. It is the force that stops you from falling through the floor, as the electrons in your shoes repel the electrons in the floor. The boson that carries the electromagnetic force is the photon, the particle of light. Finally, there is one more crucial piece of the puzzle, a particle that is in a class of its own, the Higgs boson. For a long time, the Standard Model could not explain why fundamental particles have mass. The Higgs boson, and its associated energy field, the Higgs field, was proposed as the solution. The theory suggests that the entire universe is permeated by the Higgs field. As particles move through this field, they interact with it. The more strongly a particle interacts, the more drag it experiences, and this resistance to motion is what we perceive as mass. Particles like the photon do not interact with the Higgs field at all, and therefore have no mass. The discovery of the Higgs boson at the Large Hadron Collider in 2012 was a monumental triumph, the final confirmation of the Standard Model's architecture. The Standard Model is a masterpiece of human intellect. It provides a complete and self-consistent description of the subatomic world that has been verified by countless experiments with incredible accuracy. However, as we have learned on our journey, this beautiful theory is incomplete. It does not include gravity, the 4th fundamental force. It offers no explanation for the existence of dark matter, which we know makes up the majority of matter in the universe. It does not explain the mystery of dark energy, nor does it explain why the universe contains so much more matter than antimatter. The Standard Model is not the final answer. It is a powerful and essential chapter in our understanding, but it is not the whole book. It is a detailed map of a small, luminous island of reality, while the vast, dark ocean of the unknown still surrounds it. The quest to go beyond the Standard Model, to find a theory of quantum gravity, to identify the particle of dark matter, to unify all the forces of nature, is the great challenge that drives physics today. It is the next step in deciphering the fundamental rules that govern our calm and deeply mysterious cosmos.